Welcome to the Deep Dive. Today we're diving into something pretty cutting edge in AI. We've all seen how amazing large language models, LLMs, are, right? Generating text, answering questions, even coding. But here's the question. How do we push them further? Make them genuinely smarter, more strategic for those really complex tasks? Think like writing perfect code for a competition or solving intricate engineering puzzles. That's our focus today. We're looking at a new framework. It's called Adaptive Branching Monte Carlo Tree Search, or ABMCTS for short. Basically, it's a way to help LLMs think more strategically, deciding on the fly whether to explore lots of options or drill down on a promising one. We're digging into a fascinating paper from Sakana AI, Wider or Deeper, Scaling LLM Inference-Time Compute with Adaptive Branching Tree Search and some related work. Our mission, to give you a shortcut to understanding this new approach and what it means for AI's future, is pretty exciting stuff. So let's start with the basic problem. LLMs are great, yeah, but for the really hard stuff, just one answer often isn't enough. We need the best possible answer. And that brings us to inference time scaling. It's about, well, giving the LLM more compute power while it's solving the problem, right? Making it use its thinking time better.
That's a perfect way to put it. And researchers have tried a few ways to tackle this. The paper neatly groups them into three broad categories. First, there's post-training fine-tuning, think reinforcement learning, or supervised chain of thought tuning. These try to make the LLM better at giving one good answer straight off the bat.
Okay, so improving the base model itself.
Exactly. Then, second, you have reward-guided chain of thought generation. This is more step-by-step problem solving, often used in math, where you can kind of check each step.
Right, getting feedback along the way.
Precisely. And the third category, which is really our focus here, is multiple answer generation. Here, you just ask the LLM for many different potential answers to the same prompt, and then you pick the best one.
Ah, okay. Generate a bunch, then select.
Yes, and what's crucial, the paper notes this is orthogonal to the other two methods.
Orthogonal, meaning you can combine them.
Exactly. You can use multiple answer generation on top of a fine-tuned model, for instance. They work independently, but can stack up for better results, like adding different upgrades to a car engine.
Makes sense. Okay, so if multiple answer generation is where ABMCTS plays, let's unpack the methods that came before it. What were the baselines?
Good idea. Understanding the predecessors really highlights what ABM-CTS improves. So first up is repeated sampling. You could call this the only go wider strategy.
Go wider, meaning?
Meaning you just have the LLM generate lots of independent answers from the same prompt, usually using non-zero temperature to get variety.
Like brainstorming, basically. Get lots of different ideas out there.
Exactly like brainstorming. It taps into the huge range of things an LLM could say. The more you sample, the better your chance of hitting a great solution. Techniques like best of n, majority voting, self-consistency fall under this, and it works. It's been shown to be effective on tough benchmarks like AlphaCode and ARC-AGI.
Okay, sounds pretty good. What's the catch?
The catch is it only explores. It's purely exploration. It has no way to take a promising answer and refine it using feedback.
Ah, so if it generates code, it can't run tests and fix the bugs.
Precisely. It just generates more code, hoping the next one's better. No exploitation of good candidates. Then you have the opposite approach, sequential refinement. This is the only go deeper strategy.
So this one does refine.
Yes. It takes an initial solution and iteratively improves it. It reprompts the LLM with its own output, plus some feedback like test results for code.
Okay, that sounds useful, especially if you have feedback.
Definitely. It's great for systematic improvement, but the limitation is, well, it's the flip side of repeated sampling. It only exploits.
So it just polishes one answer. Doesn't generate new, different ideas.
Exactly. It gets stuck refining whatever it started with, even if a totally different approach might be better. And finally, there's standard Monte Carlo tree search, or MCTS. People know this from games, like AlphaGo.
Right, the tree search thing. How does that fit in?
Well, it's a structured way to explore possibilities, but the standard way it was applied to LLMs had a key issue, a fixed branching factor.
Fixed branching, meaning?
Meaning, at each step, or node in the tree, it would only generate a fixed number of next steps, say 5, like in older work like LATS or RAP.
And that's bad because?
Because LLMs can potentially generate way more than 5 diverse outputs. That fixed width limits the exploration, which we saw was so important with repeated sampling. It doesn't fully use the LLM's power.
Okay, I think I see the tension. You had methods that explored widely but couldn't refine.
Like repeated sampling.
And methods that refine deeply but couldn't explore.
Sequential refinement.
And a tree search that was too rigid in its exploration.
Standard MCTS, yeah.
So it's like you either cast a wide net but can't pull anything specific in, or you dive deep in one spot, maybe missing the treasure nearby. That's the problem ABM-CTS tackles.
That's the perfect summary of the challenge. You needed a way to dynamically choose between exploring broadly and refining promising leads.
All right, this is where it gets really interesting then. Enter adaptive branching MCTS. How does it actually manage to do both? What's the magic?
The core idea, the real innovation, is that dynamic decision-making. At every step, every node in its search tree, ABM-CTS looks at the feedback it's getting and decides. Should I go wider and generate completely new ideas from here, or should I go deeper and refine one of the promising paths I've already started?
And it makes that decision based on feedback, like how well the current paths are doing.
Exactly, based on external signals, test scores, validation results, whatever feedback is available for the task. And here's a critical difference from standard MCTS. Unbounded branching.
Unbounded branching.
Yeah. It doesn't have that fixed width limitation. Remember, an LLM at non-zero temperature can theoretically generate countless responses. ABM-CTS is built to actually use that potential diversity.
How does it manage that? How does it generate more?
It introduces a special type of node called the GEN node. Think of it as an action you can take at any point in the tree. Selecting a GEN node means, okay, from this current state, generate a new child node, a completely fresh attempt. This lets it expand the tree's width dynamically whenever it seems promising.
Okay, a GEN node for going wider.
Yeah.
And then it chooses between that and going deeper down existing paths. How does it make that choice?
That's where Thompson sampling comes in. It's a Bayesian approach, a really clever way to handle this exploration-exploitation trade-off.
Thompson sampling sounds statistical.
It is. For every possible action at a node, picking an existing child to refine, go deeper, or picking the GEN node, go wider, it models a probability distribution of how good that action might be based on past results. Then, it simply samples a score from each distribution and picks the action whose sampled score is highest.
So it's not always picking the one with the best average score so far.
Not necessarily. Sometimes an action with high uncertainty, like the GEN node representing unknown new territory, might get a high sampled score by chance, encouraging exploration. Other times, a path with consistently good results will likely get the highest sample, encouraging exploitation. It naturally balances.
That's clever. Like an explorer who sometimes checks the map for known good spots and sometimes just takes a promising-looking new path into the jungle.
That's a great analogy. It intelligently manages its search effort.
But wait, is Thompson sampling itself computationally heavy? Does making these decisions add a lot of overhead?
That's a fair question. There is some overhead, naturally, but Thompson sampling is known for being quite efficient in practice, especially compared to some other methods. The benefits of guiding the search more effectively, particularly when you have a large budget of LLM calls, seem to strongly outweigh the computational cost of making those decisions. The results bear that out.
Okay, that makes sense. And you mentioned there are two flavors of ABM-CTS.
Right. The paper proposes two main variants, slightly different ways of implementing this core idea. There's ABM-CTS-M, where M stands for mixed model.
Mixed model.
Yeah. When it's selecting a node, it estimates the scores using a statistical model where different parts of the search tree, different subtrees, actually share parameters. They learn from each other in a way. And crucially, the GEN node, the generate new option, is treated as its own group, one without any direct results yet. This makes its estimated score inherently more uncertain, which naturally pushes the system towards exploring via the GEN node sometimes.
So sharing information helps it generalize, and the uncertainty of new encourages exploration. Okay.
Exactly. And when a new node is generated and gets a score, that score updates the history, propagates up, influences those shared parameters, and subtly adjusts how attractive the GEN node looks for the future.
All right, what's the second flavor?
The second one is ABM-CTS-A, where A is for node aggregation.
Aggregation. Sounds simpler.
It is, generally. It's designed to be more lightweight, without those shared model parameters across subtrees. Instead, it introduces another special node type called the CONT node for continue. This CONT node sits alongside the GEN node. The CONT node explicitly represents the action of continuing refinement down an existing child path. So it clearly separates the choice, GON, make something new, versus CONT, refine something existing.
Okay, so it separates the wider and deeper actions more explicitly at the node level.
Precisely. And the score updates are more direct. A new node score primarily backs up to the specific GEN node that created it and its ancestors.
So ABMCTSM seems maybe more statistically sophisticated with the shared parameters, while AA is lighter, more direct. Any thoughts on when you'd use which?
Well, the paper suggests Mantium might be better when there are complex shared patterns in what makes a good solution across different branches. It can potentially learn those general patterns. A, being simpler and lighter, might be preferable when computational cost is a major concern, or when the problem structure is such that sharing information isn't as beneficial. The best choice likely depends on the specific problem and resources.
Okay, fascinating nuances. But theory is one thing. How did they actually perform? You mentioned they tested these on tough benchmarks with top models like GPT-4o.
Right, the proof is in the pudding. The experimental setup was rigorous. They used live code bench and code contests. These are competitive programming challenges, really demanding logic and algorithms.
Okay, series coding test.
Definitely. Then ARC-AGI, which is about finding abstract visual patterns very different, tests more abstract reasoning.
Like an IQ test for AI.
Sort of, yeah. And MLE Bench, which uses problems from Kaggle machine learning competitions. So practical ML engineering tasks. In all cases, the LLMs generated Python code, and crucially, they used external feedback, like passing unit tests or getting validation scores to guide the ABMCTS search.
In the model.
GPT-4o run with a temperature of 0.6 and DeepSeek v3 with a temperature of 1.0. They typically used a budget of 2 to the power of 7, so 128 API calls.
128 calls, okay. And the headline result.
The headline, ABMCTS consistently came out on top. It achieved the best average rank across all these different benchmarks and both LLMs, beating repeated sampling and standard MCTS quite clearly.
Wow, okay. So it generally wins. Any specific examples that stand out?
Yeah, looking closer, on Live Code Bench and Code Contest with GPT-4o, ABMCTS just performed better. Interestingly, on Live Code Bench, it started showing an advantage even with small budgets, like just 23 or 8 calls.
Only 8 calls. That's efficient.
Right. And on Code Contest, the gap really widened at larger budgets, 25 and up. Even with DeepSeek v3, where standard MCTS did surprisingly well on Live Code Bench, ABICTS was still comparable or better. On ARC-AGI, repeated sampling was tough to beat because that task seems to really reward broad exploration. But ABMCTS matched its performance, showing its dynamic widening works well.
So it can adapt to be as exploratory as needed.
Seems so. And on MLE Bench using GPT-4o, this was really interesting. ABMCTSM, the mixed model one, was consistently strong across different ML tasks. Nomad 2018, Spooky Author, Random Acts of Pizza. The baselines, though, were inconsistent. One might work well on one task, but poorly on another. ABMCTSM seemed much better at adapting its search strategy to fit the problem.
That adaptability is key. What about how it searched? Did the trees look different?
They did. The analysis showed ABMCTS methods generally build wider trees than standard MCTS.
Wider trees, confirming the adaptive branching.
Exactly. It wasn't constrained by that fixed width. It explored more broadly when needed at different depths of the tree. But, importantly, its strong performance on tasks, where sequential refinement also does well, suggests it's not just exploring, it's also effectively identifying those really promising branches and exploiting them, digging deeper.
So it really is getting the best of both worlds, exploration and exploitation.
That's what the evidence points to. And maybe the most compelling evidence is the scaling.
Scaling with budget. What happened when they gave it more compute?
On ARC-AGI, they pushed the budget way up to 29,512 calls using DeepSeek v3. ABMCTS performance just kept climbing, getting substantially better. Repeated sampling, however, started to plateau.
Plateau, meaning more compute wasn't really helping it find better answers anymore.
Pretty much. It suggests repeated sampling gets lost in the vast search space eventually, while ABMCTS is much better at directing its search towards progress, even at very large scales. It uses the extra budget more intelligently.
Can we visualize this? Is there an example?
Yes, figure 6 in the paper is great for this. It shows a search tree for ABMCTSM on that random acts of pizza task. You can literally see the dynamic allocation. Some branches go wide early on, exploring different initial ideas. Then you see other branches that go much deeper, where it clearly identified a promising path and spent more effort refining it.
So you see both wide exploration and deep dives in the same tree.
Exactly. It's a visual representation of that adaptive, wider or deeper decision process in action.
That's incredibly cool. It feels like we're watching the AI develop a genuine strategy. But does it always work? Are there problem types where maybe this adaptive approach doesn't help as much?
That's a good question. Based on the results, it seems particularly strong for problems with clear external feedback, like code tests or validation scores. For highly subjective tasks, maybe pure creative writing where good is hard to score automatically, the advantage might be less pronounced. But for structured problem solving, it looks like a very robust improvement.
Okay, so if one LLM using ABM-CTS is this strategic powerhouse, my mind immediately goes to, what if you combine multiple LLMs? Can this framework handle a team of AI agents?
It absolutely can, and that's one of the really exciting extensions explored in the paper. It's like moving from a single brilliant strategist to a council of experts.
The Council of AI Experts.
Yeah.
How does that work within ABM-CTS?
The core idea is pretty elegant. You just add another decision layer. At each point where you decide to expand the tree, select a GEN node, you also select which of your available LLMs should do the generating. The paper mentions an algorithm for this generator selection algorithm to second, where essentially each node has multiple GAN nodes, one for each available LLM.
So the system learns which LLM is best suited for which specific subproblem or stage of the search.
Exactly. It adaptively picks the right tool for the job at each step.
Okay, that sounds potentially powerful. Did they test this multi-LLM approach?
They did. They used an even harder benchmark called ARC-AGI-2. This one is designed to be extremely challenging, less than 5% success for even the best single LLMs, really pushing cognitive ability.
Oh, wow, than 5%. Okay. And the LLM team?
They used a mix, Gemini 2.5 Pro, O4 Mini, and DeepSeek R1 0528. A combination of different capabilities.
And the results of the team up.
Pretty impressive. So running ABM-CTS with just a 4 Mini, a single model, it improved the success rate on ARC-AGI-2 from 23% using repeated sampling to about 27.5%. Still low because the test is hard. But when they use the multi-LLM ABM-CTS with all three models working together, the success rate jumped again to over 30% within a budget of 250 calls.
Over 30%. That's a significant leap on such a hard task.
It really is. And what's super interesting is that DeepSeek R1 0528, which was individually the weakest performer of the three, still contributed positively to the team's overall success.
And even the less capable model added value in the right context.
Yes. The framework figured out how to leverage its specific strengths, or maybe use its outputs as stepping stones for the others. The analysis showed this allocation happening dynamically. On easier problems where one model quickly found a good path, it got more resources. On harder problems, the workload was distributed more evenly, letting different models try different things.
True collaboration.
And the real magic of the synergy was evident too. There were problems that no single LLM could solve on its own, but the combination of models, guided by multi-LLM ABM-CTS, managed to crack them.
Wow. How did that happen?
Figures 14 and 15 in the paper show a great example. One model, O4 Mini, generated an incorrect solution. But that incorrect attempt actually served as a useful hint or starting point for the other two, DeepSeek R1 and Gemini 2.5 Pro. They then collaboratively built upon or corrected that initial flawed idea to arrive at the right answer.
That's incredible. It's like one person having a flawed idea, but it sparks the right thought in someone else. True team problem solving, but with AIs.
Exactly. It's moving beyond just scaling compute for one model towards orchestrating diverse AI capabilities.
This is clearly powerful stuff. But as always in research, there must be limitations, right, or areas for future work.
Absolutely. It's important to keep a balanced perspective. One key assumption ABM-CTS relies on is having a reliable score evaluator. You need that external feedback signal to guide the search effectively.
Right. If your tests are bad or your scoring is off.
Then the search can be misled. Developing a good evaluator can be a major challenge in itself for some complex tasks. Another point is cost. The evaluations mostly focus on the number of API calls. Future work could look at more real-world costs, latency, actual dollar costs, energy consumption for a more complete picture.
Practical deployment considerations. Makes sense. Anything else?
Well, specifically for that super hard ARC-AGI-2 benchmark, there was an interesting gap. While the pass-at-K score, finding at least one correct answer within K tries, reached 30%, the pass-at-2 score was lower, around 19.2%.
Pass-at-2, meaning selecting the two best answers to submit, like in the actual competition?
Exactly. So while ABM-CTS got good at finding correct solutions somewhere in its search tree, the final step of identifying the very best one or two to submit still needs improvement.
So the final selection mechanism needs work.
Potentially, yes. Maybe better reward models are needed just for that final ranking, or perhaps even using another LLM as a kind of judge to make a more nuanced final selection from the top candidates found by the search.
Interesting. So these aren't dead ends, but really pointers for the next wave of research, improving the evaluators, refining cost models, enhancing final selection.
Precisely. They're exciting avenues to make these powerful techniques even better.
So let's wrap this up. What's the core takeaway from our deep dive today? We've journeyed through adaptive branching, Monte Carlo tree search, ABM-CTS. It's clearly a significant step forward. It gives LLMs this crucial ability to dynamically balance exploring wide, finding new ideas, and exploiting deep, refining good ones. It makes them more strategic problem solvers.
Definitely. It moves beyond the limitations of just sampling or just refining.
And the value for you, listening. You've got an insight into how AI at the cutting edge is becoming more capable, more efficient, and frankly, more intelligent in how it tackles complexity. This isn't just incremental improvement. It feels like a shift in capability.
It enables them to handle harder problems more effectively and use computational resources much more wisely.
So here's a final thought to leave you with. We've seen how this adaptive thinking, deciding wider or deeper, and even the collaborative multi-LLM approach can revolutionize coding and abstract reasoning. Now, project that forward. Imagine applying this adaptive collaborative AI approach to other grand challenge domains. What about accelerating drug discovery? Or untangling complex climate models, designing revolutionary new materials, even aiding complex strategic planning, or maybe composing sophisticated music? What previously unsolvable problems requiring both broad creativity and deep refinement, might now finally be within reach. That's something to ponder. We'll definitely be keeping an eye on where ABM-CTS and similar ideas go next. Thanks for joining us on the Deep Dive.
Thanks for having me. It was a fascinating discussion.
Until next time, keep exploring.